you very much.
You're welcome. Okay, well, thanks everyone for coming here. We are glad to announce the second IC seminar with the visit of Professor Jürgen Blum, that has been for many years a close collaborator, really enthusiastic about the physics of minor bodies in the solar system, starting from the growth of grains until big bodies, no, like can be asteroids, comets, and so on. Okay, Professor Blum just made the studies in physics in Gießen University in the 80s, and then moved to Heidelberg to get the PhD thesis in the 1990s, and then habilitation in Jena University. Since then, has been first of all in the 1987 until 1992 was at the Max Planck Institute for Nuclear Physics and Technical University of München. Then from 1992 to 1996 at the Max Planck Research Group Dust in Star-Forming Regions at Jena. Then moving to the 1997 until 1999 at the Astrophysical Institute of Jena University. And then moved to the Department of Astronomy, University of Florida, and Naval Research Laboratory in Washington, D.C. Then to the Jena University again until 2003. And since 2003 to nowadays, is professor at the Technical University of Braunschweig. And well, we are really glad having you here. And please go ahead with your talk. Thanks for coming.
Can we switch? No, minimize. Can we minimize that?
Okay.
Yes, there we go. I need the pointer. Oh. So thank you very much, Josep Maria, for the kind words and for the invitation to be here. I'm really happy to be talking to you today in my seminar talk, or colloquial talk, and later on in individual talks, if you like. So my field of study is the formation of planetesimals, and if you have never heard that word before, I briefly explain. This consists of planet and infinitesimal, and everybody knows who has studied mathematics that infinitesimal means very, very tiny. So these are very tiny planets. So the precursors of the nowadays planets, but of course we are interested in learning about those objects, not only by doing experiments or modeling, but maybe there are planetesimals left over in today's solar system. Maybe comets are one of those. I'll ask that question a bit later again. So I'll have basically two parts. The first part is how planetesimals form, and the second part is about comets. And I guess many of you have not been studying the formation of planetesimals, and this is why I give you an extended overview of my personnel. You see, it's one of my review papers here. One of my personal view of how planetesimals form over time. What you are seeing on the top, I have a pointer here. So on the top is a time axis. So starting very early after t equals 0, whatever that is. So some people believe that t equals 0 is where the calcium aluminum rich inclusions, which we find in meteorites, is, but doesn't matter. Any t equals 0 means within 100,000 years or so this happens, and then within a few million years that happened, and after 10 million years this has happened, and then a long time goes on until today, 4.5 billion years after t equals 0 is where we are today. And you're seeing there's 5 different types of planetesimals that may form. But I'll go into the details here, explain every step. So we start with the first step, from dust grains to planetesimals. So the start is at about a micrometer in size. So this is the typical canonical size of protoplanetary disk. Dust, roughly a micron, maybe 100 nanometers or so, doesn't matter very much in the end. And we go through various stages of dust coagulation, collisions leading to sticking or not sticking. And in the end, we're forming what we call pebbles. And I will show you examples how we study that phase here. And that we did that traditionally in my group by doing experiments, lab experiments, or in that case, microgravity experiments, because in the lab, everything falls down very rapidly because the gas environment has to be a rarefied gas, so vacuum or very thin gas. So things fall down very quickly. And in order to prevent that and to be able to study dust coagulation, we regularly go into microgravity. I play that video in a second again. What you're seeing here is a stereo view. Left and right is the same thing from 90 degrees apart. And we highlighted with this brighter part in the inner parts an agglomerate that we originally put there. So this original agglomerates were like this. So you're seeing the size, 100 micron, give or take. Each of the clumps, again, consists of, you're seeing that, micrometer size silica spheres. Just to have a clear growth stage from the silica spheres, we go to 100 micron clumps. And here in the video, we go from 100 micrometer clumps to centimeter particles or so by individual collisions. You're seeing the collisions either left or right, same thing. And you see we have hit and stick. So the particles come together, typical speeds here on the order of a few centimeters per second. Absolutely realistic to what people think in the protoplanetary disk happens at 1 AU or so. So again, originally the clumps were 100 microns, consisting of micron grains. Silica is the material here. And finally, we achieved centimeter particles. We did literally hundreds of those types of experiments and different ones. And in the end, after really many, many experiments and decades of work, we ended up with a dust collision model, which is very complicated, as you can see here. So I'll explain what you're seeing here on the x-axis. It's the size of an aggregate growing from microns in the lower left corner to possibly to large sizes. On the y-axis, the same axis. So two particles come together at the speeds indicated at the contours in meters per second. So 1 meter per second would be that. Here's 1 meter per second. 10 meters per second is here. And the four panels indicate different grain sizes and different grain materials. So here's micron size silica at 1 AU. Here's 100 nanometer silica at 1 AU. Here's water ice at 3 AU. Here's water ice, micron size water ice at 10 AU. So the principal plot is the same. The contours change because there is a protoplanetary disk dust collision model behind. And the most important things are the colors here. So you're seeing greenish colors, and green means sticking. So it's good if you want to grow. You're starting in the lower left corner, you want to grow. You can either grow this way if nature permits. So this way would mean you grow a body very large by collisions with small bodies. But unfortunately, if you want to consume small bodies in growing large ones, you empty the reservoir of small bodies. So usually the growth goes in the diameter. And then is what is happening is you're hitting the yellowish or reddish regions, and yellow is bouncing, so no longer sticking. And the red is even bad, is even worse. It's fragmentation. And I just want to stress one little corner here is the erosion barrier. It's symmetric, we find that here as well. And the erosion is like sandblasting. So you're having collisions between very tiny grains here and large grains there at speeds, if you look at this contour, above some 10 meters per second. And imagine you have a dust clump consisting of micron-sized particles, and you hit it by micron-sized particles on the order of tens of meters per second, you erode the large body away. And in this work, and this is why I show this plot here, in 2018, we painted the whole thing green, except for this corner. So we allowed every collision to lead to sticking, except for this little erosion thing. And you're seeing here, so we have a mass, this is size, This is a frequency of occurrence. We start at early times, and the time evolves, so we're growing and growing and growing, and then suddenly we stop. And the maximum size we can reach is 10 centimeters. So even in the case that you ignore all the fragmentation events, I'll show you a video later, all the bouncing, ignore all the physics, and only allow the erosion, the maximum size we could grow in the protoplanetary is on the order of 10 centimeters. This is, unfortunately, nothing better is possible. Well, this sounds bad, but in the end it isn't. Unfortunately, the title has vanished here, so I need to move this to the lower corner. Okay, so how large can dust aggregates grow through collisional sticking? And this is the first paper, first two papers back to back, in which we address this question. So that is a little earlier than the lightest model I showed you, but it doesn't matter. So it's from 2010. And I show you those two papers because we coined, I think we coined the term pebbles, which everybody uses now. So these are the two papers that invented the term pebbles for which something that is not a pebble, but not a stone, but a dust aggregate. I'll show you a little later. So I'll show you results from that paper here. So this is that plot as a function, for instance, the turbulence strength in the protoplanetary disk model at 1 AU. In that paper, for actually 3 protoplanetary disk models, we could show, plugging in all the physics known at the time, that we can grow bodies on the order of 1 gram. Here, this is the mass in gram, 1 gram in size, regardless of the turbulence. So 1 gram in size is give or take a centimeter or so. And this is what we call a pebble, because pebbles are centimeter size bodies on a beach, for instance. We've worked more on that in a later paper by Sebastian Lorek et al. As a function of heliocentric distance. So this was at 1 AU. Here we go out to 50 AU for 2 different sizes of the dust. Dust ice, actually, here's microns, here's 100 nanometers. We could show we can grow in the inner part of the protoplanetary disk, again, into the gram region, so centimeter particles, in the outer protoplanetary disk into the milligram region, millimeters. And this is why I wrote here, outer solar system up to millimeters is what we do physically understand. And others have followed. So Dominic and Philemon reach, well, slightly smaller sizes to Björn with his model that builds a lot of on our physical results from the experiments, also ends up at centimeter in the inner protoplanetary disk and millimeters in the outer disk. So at this point, we believe we can understand the growth from submicron micron particles into what we term pebbles or point pebbles, centimeter to millimeter particles. The question is that realistic? And fortunately enough, as of a decade ago or so, we have ALMA, and ALMA with its superb resolution, spatial resolution at long wavelengths, can resolve protoplanetary disks. And there's many, many works on the dust side. In the second row here, you're seeing 7 disks. These 3 here at the bottom, these 4 at the top. And here's a centimeter, here's a millimeter, and throughout the disk, you are seeing those observations indicate that the dust sizes are on the order of centimeters in the inner disk and millimeters in the outer disk. And a particular disk that is also here has been studied more extensively by these authors here. And they applied, of course, there's lots of modeling to interpret the dust size. They adopted 2 models, agglomerates that are compact and agglomerates that are very fluffy. And you are seeing here's again a centimeter in the inner 40, 50 AU centimeters, in the outer is millimeters or so. And here it's slightly different, very different in this particular ring here. I don't know which model is the best one, but give or take, they are the pebbles. Yeah. Is there a question? If you have any questions, please shout in. Just it's fine. Okay, so that's the first step. Here we are at pebble sizes. But of course, we want to make planetesimals. And when I started the field like 35 years ago, my first experiment showed that the aggregates don't stick, but they bounce. So the bouncing barrier, which we call the threshold that determines the centimeter pebble size in the inner disk, has been a worry until some decade ago, when people got to the idea that we don't need to grow planetesimals from dust onward in just one successive step of sticking collisions, but there are other methods. So what we're seeing here is we have the pebbles, and there's some dust amongst the pebbles, and we have an effect called the streaming instability, which concentrates the pebbles spatially without changing them. And the concentration is such, enhancement, the factor is so high that the collective gravity of all the pebbles is sufficient to clump them together and form what we then call planetesimals. The advantage of that is the timescales here are extremely short. We are talking about a few 10 orbital timescales. Instead of, if you want to have sticking events, it would take maybe 1 million years or even longer to form planetesimals. And that what was a problem all the time, no longer a problem now. I'll show you the details here. So we have, in the end, a gravitational collapse of a cloud of pebbles, but how do we get them to be concentrated? And I'll show you 2 movies from Jake Simon. So this is without gravity, just to show you the clumping by pure hydrodynamics, so no gravity, no magnetism, nothing, just pure hydrodynamics, and then we'll switch on gravity and show you how that acts on top. So what we're seeing here is a view on face on, so it's x direction. This is the radial direction. This is the azimuthal direction. We are co-rotating, so this is Keplerian shear inwards. This is Keplerian shear outwards, and the color, as you see, is the log in the overdensity or underdensity. So it's negative. I think I'll stop that at some point. Let me give a second. Maybe I stop it here. So the underdensity goes, it's logarithmic, is almost a factor of 1,000 below the typical 1 to 100 dust to gas ratio. And on the other end, it's almost a factor of 1,000 above. And you're seeing those red dots here. These are concentrations of clumps of pebbles by pure hydrodynamics. So what's happening here? I think it starts again. Yeah. So we're starting evenly, and a single pebble, if it's immersed in a shearing disk, because it's gravitational, it's Keplerian shear, plus it does have a pressure gradient from the outside to the inside, so it's a bit sub-Keplerian. A single pebble experiences a headwind. So the single pebble wants to be on a Keplerian orbit, but it's not strong enough by itself to, like a planet, to pass through the gas. So it feels friction with the gas and tries to radially migrate inward. When 2 pebbles come together, they can arrange one past the other. So the first one takes the drag and the other one does not experience the drag anymore at the full strength and kicks the first one. So they collectively go faster together. And that means they catch up with a slower one. So they form a triple. And the triple forms a quadruple and a quintuple and so on until a large clump forms. It's like a peloton in a bicycle race. So the front 4 peloton bike riders take all the headwind, and the hundreds of bike riders behind them are in free flow. So they're without headwind. So they can save their force and power. And of course, those front people don't do that all the time. So they go on the back and relax a bit. And here is the pebbles. The front pebbles are always pushed by the back ones. And so the stream of collective stream of pebbles becomes more and more intense. And at some point, of course, then gravity kicks in. And this is basically the same simulation plus the collective gravity of all the pebbles. And what you will be seeing here is that planetesimals form, and those planetesimals even interact and merge is like, it looks like a bit like galaxy mergers at some point, but it's pure hydrodynamics in that case. And in the end, planetesimals with a canonical size of give or take 100 kilometers form. I want to talk about comets later on. So comets typically are smaller, with exceptions, are smaller than 100 kilometers. This is a matter of numerical resolution. As the resolution gets better and better, people find the 100 kilometers is still stable, but there's a tail of smaller planetesimals forming into the resolution limit, which is at the moment 10, 20 kilometers or so. So I'm pretty sure also bodies of cometary size can form. And this is my personal picture of how a planetesimal, or in that case, a cometesimal, looks like. It basically consists of many, many pebbles. But pebbles would have size distribution, and there might be dust in between, but I don't want to talk about that today. Okay, so this is now the second step. We do have the planetesimals. They might have different sizes. So there might be the big ones, the 100-kilometer objects, and the small ones. The big ones will undergo will experience inner stresses that are much larger than those inner stresses of the small planetesimals, and that will lead to a mechanical differentiation. And we studied that. So we formed kind of a pebble pile. So each of the clumps you hopefully will be seeing here is a millimeter aggregate of silica dust. The individual dust particle, again, is a micron or so in size. And we formed a pile of pebbles in a cylindrical shape and exerted pressure onto that pile. And what I give here is one of the few formulas I will be showing is this is the lithostatic or hydrostatic pressure in the center of an object, which radius r, and some average density, of course. So it's 35 pascals for a body of 1 kilometer radius. It's 3,500 pascal already for a body of 10 kilometer radius, and so on. So here's 1 kilopascal, here's 10 kilopascal, and 100 kilopascal. So we're talking here in those pressures about objects on the order of 10 kilometers and larger. And we measured in the lab for different constitutions of the pebbles the volume filling factor, which is 1 minus porosity. So it's the actual volume filled by matter, starting roughly at 20%. And we saw if we go to larger and larger stresses, pressures, so in reality, going to larger and larger planetesimals, we increase the volume filling factor almost by a factor of 2. And that has consequences for cometary activity. I will be talking about that on the next slide. So again, the same plot here. Back in 2014, we did experiments with pebble piles like those and compressed them. And with the same pebble piles, we measured the tensile strength, which is shown on the y-axis here. So as a function of the compression, now 1 kilopascal is here. So again, the formula, a 10 kilometer body would be 3.5 kilopascal. So 10 kilometers would be here. So we're in the 1 to 10 kilometer body range, where the pressures are little. So the compression is also little, but here the tensile strength is shown. And the tensile strength for uncompressed millimeter pebble piles by van der Waals forces is on the order of 1 pascal. So this is not 0, this is 1. But as we go from a very tiny planetesimal to a 1 kilometer object, we're going through higher tensile strength. And that is important for the topic of dust activity in comets, because cometary activity only works as we understand them if we're here. So if a comet was born as a large body, and of course would have been eroded towards its center, these tensile strengths would be way too high in order to be active. So that is also one of the big questions in cometary research. When do comets die? And that touches that field. Okay, so we distinguish between large planetesimals, give or take 100 kilometers or so, to 10 kilometers, and small planetesimals. The large ones are stratified mechanically, the small ones aren't. So the next stage is, immediately when they are formed, they may set free radioactivity because they inherited short-lived radionuclei. So SLM means short-lived radionuclei. So radioactive nuclei like aluminum-26 or iron-60 or something like that with a half-life on the order of 1 million years. Inherited by the young protoplanetary disks. We know that from meteorite research, so that Maria can talk about that for hours probably, inherited by in the formation process by whatever AGB star supernova, which went on shortly before our planetary system was formed. And now what happens if I have a body that looks like this here, and I release radioactive heat? And that is also very important for comets. So we have a makeup of a planetesimal like that, and we release heat. So if we want to get rid of that heat, we have to transport the heat to the surface. And the transport property is the heat conductivity, which is given here on the y-axis as a function of temperature. The point is here, this is a pebble. So the pebble consists of micron dust particles with a very low heat conductivity itself. But here we have a planetesimal consisting of intact pebbles, because we're talking about small planetesimals. And the heat transfer from one pebble to the other is very, very minor. So extremely small. We are talking about values of the order of less than 10 to minus 3 watts per meter and Kelvin. If you're familiar with heat conductivity, and a typical material has values between 1 and 10. So we're down by 4 orders of magnitude. So there's absolutely no heat to be transported here. This is 0. The air has the heat conductivity of here. So we're a factor of more than 10 below the heat conductivity of air, if the temperature is low. If the temperature is high, you see a steep rise, because then the radiative term, which goes as temperature to the power of 3, kicks in. And we calculated what happens if we release heat in the volume, and how the heat is transported outwards, and how an icy planetesimal would react. We were not the only ones. So the first one was Jürgen, who did in 21 a calculation what happens with different ices as a function of depth. So the whole body was 35 kilometers in radius. Zoom into the first 5 kilometers from the surface, and zoom in from the first 200 meters. So there is differentiation in the ice. And we looked more intensely into that, assuming isotopes, or like already mentioned, aluminum-26 and iron-60. Here are the half-lives or decay times, and the abundances, and then the energy release. And for, as one example, for a planetesimal of 10-kilometer radius that was formed 5 million years after CAI, because the formation time is important here. As we form earlier, the inheritance of radioactive nuclei is bigger. If we form later, they have already decayed before they are incorporated into a planetesimal. So in this one example, we show the water abundance. Here, the original water abundance was 0.1 in these units. And after the decay has happened, we have reduced the water abundance by more than half in the inner, 8 kilometers out of the 10. And all the water has been deposited just short of the radius, because the outer radius is cold again. And we did that for many, many radii, so starting at a half, up to 20 kilometers at many different formation times, 4, 5, 6, 7, and so on, million years after CAI. And the pie charts here tell you what percentage of the body's volume exerted temperatures given at the limits here. So the black is below 70 K, never heated. You see 70% is, if you have a very small body, and it forms very late, all the radioactive nuclei basically all have decayed, and everything stays low in temperature. But if you go to larger bodies and earlier formation times, it becomes whitish, and white means even higher than 273 K. So in principle, water can even melt in a body big enough and forming early enough. And what happens if water melts inside a pebble pile is what we've just studied for fun in the lab here. So here's icy pebble piles. So we mix silica grains with micron-sized water ice grains, form pebbles and a pebble pile, let it thaw under 273 plus a little bit ambient temperature conditions, prevent the gas from disappearing by having a lid on the glass, and just watch. And the water does not just melt, but it destroys the pebbles. So the inner parts of the planetesimal can even collapse with consequences that we haven't looked into yet. So that is what we're just trying to do here. So in the end, it matters how large a planetesimal is and how early or late it formed, whether it remains pristine in its volatile abundance, so then it's blue all over, or it is depleted, which is the color red here, in its center, and the volatiles are all deposited at a higher abundance in a small annulus above that, and of course the upper surface is completely pristine. Okay, so that's was step 4. Step 5 now. So step 4 was 10 million years. Now we have 4.5 billion years to park the planetesimals somewhere if they are to survive until today. So if they were parked in the terrestrial planet-forming regions, they were destroyed by being consumed by Earth, Venus, and Mars and Mercury forming. If they were parked in the asteroid belt, only the big ones have survived. They are still planetesimals, but the big ones lose memory of everything because of all the metamorphisms I talked about. If they are further out, the giant planets consume them. And if they were parked in the Kuiper belt, then they might still be there. But being still there, meaning we have collisions to take into account. And collisions are severe here. So what we've done here is an experiment in our little laboratory top towards its vacuum. We shoot a pebble pile looking like that upwards. Let the second one drop down. They collide at this case at 10.7 meters per second and completely destroy. So this is fragmentation at very, very low speed. And you can imagine if two planetesimals whose makeup is like that colliding in the Kuiper belt, where the collision speeds are on the order of several hundred meters per second or even a kilometer per second or so, they might also be destroyed. So only those that are lucky enough to undergo subcatastrophic collisions will remain intact, more or less. They might be eaten up or so. Those undergoing catastrophic collisions, so let's start here. Those undergoing super catastrophic collisions are completely destroyed, even molten, and completely forget about their past. And those in between, they might not be heated enough, they might not be compressed enough, but they're losing their structural information. So they become rubble piles in the air. So we distinguish because we have no idea about the actual collision behavior of kilometer-sized bodies made out of pebbles. So this is the work going on. So we distinguish between subcatastrophic, catastrophic, and supercatastrophic collisions. We distinguish between planetesimals that do not undergo differentiation of the volatiles or do, and we distinguish between small and large planetesimals that the small planetesimals are not mechanically differentiated, whereas large ones are. And this leads us to the distinction between 5 different potential types of planetesimals that could be found today in the solar system. And of course, we look out for those that resemble comets best. So those are the super lucky survivors of everything. They were small enough not to be compressed, small enough not to be differentiated in the volatiles, lucky enough not to undergo catastrophic collisions. Those have no catastrophic collisions, but thermally metamorphosed. Those not thermally metamorphosed, but undergoing catastrophic collisions, forming pebble piles. Combination of the two is here, and those we can forget about because they don't teach us anything. Okay, that was my first part. Now you know everything about my idea how planetesimals form and in what shape they would be today if we were to find them. Now let's consider comets. So I have two parts here. I hope I have time for both. The first part is the most important here. I'll try to convince you that we do have lots of evidence that comets do indeed consist of pebbles. That would be a striking evidence already that comets formed by the process of first coagulating dust into pebbles, then collapsing a pebble cloud to form planetesimals, and here we are. So there's three lines of evidence. So I'll start with astronomical observations, go to meteor showers, and then missions. Here's a beautiful picture of a comet. We'll be talking about the dust tail in the second part, and about the dust trail, which you are not seeing here in this first part. So dust trails of comets. You might not have heard of that expression if you're not an observing astronomer. Dust trails were first observed in the 1980s when the infrared sky was mapped at the first time by the IRIS satellite. So the IRIS was a US UK coordinated program to map the sky in thermal infrared for the first time ever. And people were surprised to see linear trails across the sky, like those you are seeing from airplanes. So the chemtrails, if you like. There's chemtrails in our solar system everywhere. And people then recognize, oh, these coincide with the orbits of comets. So comets do expel material. A little bit of material goes into the tail. So this is little dust. I'll come to that point later. Of course, here's the gas, which is then ionized and becomes the gas jet. But most of the material goes into the trails. And that most material is distinguished by this beta parameter, which is the ratio between the radiation pressure of the sun relative to the gravity of the sun. And if you're looking at, I deleted that picture. So if you're looking at a cometary tail, you will be seeing that in the tail, the beta parameter is close to 1, so between 0.1 and 1. And 1 is roughly a micron in size, and 0.1 is 10 microns. Whereas 10 to minus 3 is millimeters, and this is smaller than 10 to minus 3, so it's millimeters and above, where most of the mass goes. So these millimeter and larger particles are ejected from the comet at extremely low speeds, just above the escape speed. And that means they stay on their orbit, on the orbit of the comet, but radiation pressure pushes them slowly along the orbit because it just slows them down a little bit. It reduces gravity by this fraction. So they are slower on their orbit. So they spread all over the orbit and are identified as cometary trails. So most of the cometary trails particles are larger than a millimeter and contain most of the ejected mass. So this is millimeters, we've heard, or larger is the pebble size. Then these are closer to pebbles and not real pebbles like solid rocks. Can be seen, for instance, in this picture here. This is a paper by Peter Jeniskens and co-authors from last year. And Peter, like Josep Maria does, has studied meteor showers a lot. And meteors are those bodies that enter the Earth's atmosphere and seen as these incidences that you can occasionally see on the sky. But at some times per year, Earth crosses a cometary trail just by chance. And then you see many meteors per minute or per hour instead of a few. That could be hundreds or even thousands or so, depending on the resolution you're having. And in Peter Jeniskens' paper here, they also determined the density. And a solid pebble would have density on the order of 2-3 grams per cc. There are some here, but most of them are well below the density of 1. So they must be fluffy, large and fluffy. So they are large. Here's a centimeter. Canonical size is centimeter. Density is below a gram per cc. Voila, here we are. We have the pebbles right in front of us. The particle sizes are right. The densities are right. The tensile strength, Josep Maria has worked a lot on that, is in the kilopascal range, which is exactly what we would expect from dust pebbles. And there are some differences between different types of comets that are detailed. And the third line of evidence we're having from missions to comets. So there's been many missions now, starting in the 1980s, I think, with Giotto, then Stardust, Epoxy, Rosetta, you name them. And Rosetta, of course, was a full-fledged mission, being at a comet for more than 2 years. And we, back in 2017, compiled the data from different Rosetta instruments, which are here in this range. And here's the size. And different instruments constrained the dust sizes expelled from the comet by different methods. So, for instance, the Miro observation at the radiometer constrained the sizes between millimeter and centimeter. The Lupus TM was on the Rosetta lander, not much constraining it, and. So here is the observations from Rosetta. Here is what the streaming instability needs in order to work. Here is the models for the dust formation of the pebbles, and all agree in this short hatched region here, which is give or take half a centimeter in radius. So 1 centimeter is obviously the canonical size of the particles expelled by Comet 67 P. Churio Modgara Cement. So we have that size, and that was confirmed later by another work. They seem to have a microporosity of 50%, plus minus 10%, give or take. That will play a little role a little later. People have tried to measure their composition. So Fuller and co-workers argue they have little ice, and the refractories consist of 2% of sulfides, about a third silicates, and 50% of hydrocarbons. And from the refractories, Bodin et al. Argue it's half-half between minerals and organics. So this is their tripart from their paper. So this is an astonishing result, I think. So we have 50% in mass in the minerals and 50% in mass in the organics, which is a lot. And Marco Fuller and al. Also argued that these pebbles must have some internal structure, not only consisting of micron-sized, but consisting of aggregates of micron-sized particles. So here are the particles, here are small aggregates, large aggregates, because only those internal structures, like shown here in this plot, can explain the measures, which are the boxes, the water emission from the comet. And here's the model that explains that from Chamiello et al. 23. But that is completely under debate here. So whether that internal structure is really true or not. Okay, the second part about comets, if you give me a few more minutes, is the question, why do they have tails? So I've shown you a picture already. Here's another very beautiful picture of a comet with a beautiful tail. But I asked myself, ever since I've been studying comets, why do they have tails at all? Because we know, this is the picture I wanted to show you earlier. Here's a cometary tail, and here's the beta values I mentioned before. So these are micron particles. Here are the particles 10 micron, here's 100 micron. So basically, all the small particles in the tail are micrometers. And here's the trail, and here are the beta values that are very, very tiny. So these are millimeters or larger. So the micron particles that are in the tail, they should possess cohesions on the order of 1 to 10 kilopascal. I show you a picture here. So some work from my lab from last year as a function of the volume filling factor, 1 minus porosity. We measured the cohesion inside, and as I mentioned before, Josep Maria has measured the tensor strength of meteor showers, cometary origin meteor showers, and the canonical value in the kilopascal, which matches very well with what we're finding here. And as a function of grain size, we find that. So kilopascal is here. So if it was a kilopascal at 50% porosity, we would have grain sizes of a few microns. It's 10 kilopascal, they could be 100 nanometers. This is the range we're talking about. So we have cohesion on the order of kilopascal. But if you're doing work on the gas pressure, that is in a classical model by Kurt and Keller 94, responsible for driving out the particles, releasing the particles against their cohesion. Then if you're doing a model like we did back in 2012, but all the new models come basically to the same results, the canonical pressure you're getting is 1 Pascal. So short by at least 3 orders of magnitude. So that's the question, why do comets have tails? And until a few years ago, I had no answer to that, but now I do. Because I mostly do work in the laboratory, we set up a big comet simulation. We built up a new lab called COFI Lab, the Comet Physics Laboratory. And the first work we've done was not studying some mixture of ices and minerals and organics and making it complicated. We wanted to start simple because it's Comet Physics Laboratory. We wanted to understand physics. So what we did a comet simulant consisting just of ice. What you're seeing here is an electron micrograph, and you cannot read that. So this is between the two of those things is 2 microns. So the typical diameter of the ice particles is 5 microns. The sample is just ice, nothing in it. Granular, microgranular ice. A cohesion, again, is a kilopascal. And what we're seeing, I show you a video first, and then I discuss the picture, is if you look at it, shine some artificial light on it, so mimicking the sun, you occasionally see particles flying off. It's dust active. There is no dust in it. It must be ice particles. There's nothing else in it. It's just ice. So we can switch it, the lamp on, it becomes active, we switch it off. It's inactive, we switch it on again. It goes on forever and ever. We did that over many, many hours. You see how the dust comes out, exactly where the sun shines in, brings energy into and heat, of course. And we measured the mass of the sample as it reduced and calculated the mass as it should reduce by measuring the surface temperature by evaporation. And the difference is on the right-hand side, the fraction that goes out in particles. So this band here, the data point, is a fraction between 20 and 40% that go out in particles. So why the heck is that? Now, this is exactly the dust activity we were seeking for, but not dust, but it's ice. But still, the cohesion is kilopascal, and we're seeing them being emitted. And the answer is very simple. So imagine we have a size distribution of ices. Everything is ice, regardless of whether it's blue or not. And we have the top 1,000 layers or so are more or less isothermal. We calculated the optical absorption of the light, and the first millimeter or so is isothermal. So this is all the same temperature. And of course, then, if it's all the same temperature, the small ice particles like this or that or this or that, they evaporate faster than the large ones. So they go away. And this is the lower picture here. So they have gone away, leaving back this blue part, which has no contact. So there is absolutely no tensile strength to overcome anymore. And we calculated in a simple model, numerical model, by creating that. I'll show you a movie, or 3 movies actually, of that in just a second. As a function of the volume filling factor, what would be the fraction of particle release? And we've seen the experiment between 20 and 40. And this is about the volume filling factor we're having in our sample. So that all matches. As we have a model that works for pure ice, we thought, well, let's apply that model to a comet. So now the colors mean anything. The red is a dust particle, the white is an ice particle. So the makeup of a comet is a dust-ice mixture, but we have no idea whether it's a mixture of what we call an intimate mixture of dust particles and ice particles, or whether the ice is on the surface of the dust, which is the right-hand side. Again, we evolved from top to bottom, evaporating the small ice particles first, evaporating those with the thinnest ices layers first, and follow the emission. So let's do that in some movies. So the blue color is dust, the yellow is ice. It's periodic boundary conditions. So this is just 1D depth, and the rest is periodic. And you see, this is dust active all the time. So the ice evaporates, the dust is being emitted by, of course, there's a gas flow. like in a cometary surface. For a dust ice coating, that naturally also goes. Color means the size here, because every particle is coated in ice. Also, that is active until the whole sample is gone. If that was the case, the comet would expel all its dust mass into the tail. It only expels a small fraction into the tail. Why is that? Well, we varied the dust to ice ratio. Again, the blue is the dust, the yellow is the ice. And here we are. Here is an inactive part of a comet. So there's too much dust for the ice to overcome the cohesion at some point. There's always bonds between dust particles left over. So that's the idea here. And it turns out this cannot be the case for comets. So comets cannot be core metal particles because they would expel all its dust into the tail, which is not what we observe. It can be like that, but a small amount of dust is only expelled if most of the volume of the comet has a dust to ice volume ratio of 3:2 or a dust to ice mass ratio of 3:1 roughly. Okay, I think I'm lacking time, so I'll yeah. And I come to that point. Oh yeah. So 3:2 dust to ice volume or 3:1 dust to ice mass ratio at least. Most of the Comet 67P at least seems to be that dust to ice ratio in excess of 2 or 3. But there are a few points called the webs, water-enriched blocks, which seem to have a dust to ice ratio of 2, which is below that, but a few percent is fine. That is the dust that goes into the tail. And here you see the white spots that partly even survived over weeks or even months, identified in the comet, in Comet 67P, long-living, blue in color, so ice-rich, water-enriched blocks. And I interpret them as the sources of the dust in the tail. And the rest of the comet, which is most of the surface and most of the volume, is completely inactive in terms of providing dust to the dust tail. They only provide the pebbles to the trail because they are expelled by carbon dioxide. Okay, so I go over that. So my conclusion is comets seem to consist of centimeter-sized pebbles. Fine for the formation model I explained you earlier. Comets seem to be slightly inhomogeneous. We can discuss that if you have a question about that. Most of the ejected cometary dust mass is located in the trails and can be studied by observing meteor showers, and I can only encourage people to do that more. And here's a striking picture of the Rosetta lander camera. What you are seeing here might be the pebbles on the surface of the comet. The resolution here is just a few millimeters, so this is the right size. I come to the end. So a comet nucleus analog is a comet has a low packing density, is relatively homogeneous except for the web. It has large pore space among the pebbles. It has very low strength. A pebble pile has a strength of 1 Pascal or so, and it has a very low heat conductivity, and it is resembled very well by a heap of sand. And unfortunately, if you this is a nice quote from the New York Times back in 2020, explaining the complexity in physics. Newton's law is something we think we understand. Well, it becomes difficult understanding special relativity, more if it's going to gravitational effects, general relativity, or quantum mechanics, but this is the takeaway point. Stand is completely non-understood. And with that, I would like to stop the talk. This is the picture of planetesimal formation. These are my acknowledgements, and thank you very much for your attention.
Thank you so much, Jürgen. Time for questions then. Ian,
question and comment. Sorry for the opinion. So a few weeks ago or a month ago, I saw a paper on Venus. One of my instance of comet is one of your type of comet that is not, I think the said in the paper that there were a lot of hydrocarbons and rather complex ones. And one of the ways to form these hydrocarbons was that they formed into a larger body that probably has more water. So can you explain how Venus fits in the picture? Because many of these hydrocarbons were even close to things that are in the area.
The Venus origin is in the asteroid belt, and the canonical collision speeds in the asteroid belt are between 3 and 5 kilometers per second. So they would fall under this category here, non-icy rubble pile type, whatever. So I think it's true that most of the small asteroids are rubble piles because they, and rubble pile is an indication that there was a catastrophic collision where things were torn apart, things were compacted, and then parts came together to form the smaller asteroids and families of asteroids also. So I think Bennu is in here, and we cannot learn about the pebble structure a lot because the individual rubbles are so compactified and devoid of ices that unfortunately those planetesimals that formed in what is today the asteroid belt had too high collision speeds, and they were always super catastrophic as long as the bodies were not larger than a few hundred kilometers. So
Significantly depleted by collisions.
Yeah.
Contact.
So the Kuiper belt is the only way to look in situ for surviving planetesimals.
The explanation that you give for the comet tail, does it work also when comets are recurrently coming to the solar system? Because this would seem that once they pass a couple of times, deplete, you use this explanation to deplete all the ice, and then that's one.
Yeah, I oversimplified the case. Thank you very much for the question. What I looked into is the surface of a single pebble. So this is my picture of a single pebble close to the surface. It is either active, so yeah, this would be active, or it does have so much dust that the dust percolates, and then the ice goes down and leaves what we saw in this movie, leaves the dust behind. But at some point, I show you the movie again. This is the surface of a pebble. At some point, you reach the bottom of a pebble, and then a new pebble starts having ice again. And that pebble can be expelled by gas pressure from CO2 from below, and renewing the surface also in water ice. So this is what can happen if a comet comes back after one revolution about the sun. But this needs to be, of course, modeled in detail, and we have only started here. So it's certainly a valid question. Can this model explain the repeated reactivity of a comet when it comes by next time? Yeah.
The meditation, because comets over times of centuries or thousands of years,
yeah, they become inactive at some point, and that was what I showed you before, the tensile strength picture. If the original body was large enough, the inner parts suffered suffered lithostatic compression, increasing the tensile strength. And to overcome the tensile strength, in order to get rid of the pebbles, the gas pressure by the CO2 ice or CO ice, whatever you want, has to be large enough. And that is not possible if the tensile strength exceeds 1 Pascal or so by a large factor. And then they become really inactive forever.
I had one question. So I'm a total outsider, so maybe it's a stupid question, but what would be the effect of electrostatic charges in the small particles, or between larger pebbles and smaller particles, if the charges are different or equal? So
yeah, you're referring to the formation of pebbles.
Yeah,
like in this phase.
Yeah.
Yeah. This can go in two ways. First of all, if you that depends on the sources of charging. If the source of charging is some cosmic rays or background radioactivity or whatever, then all the grains are charged with the same sign, because the radioactivity, cosmic rays charge basically the gas, and the electrons in the gas are more mobile than the ions, so that all the particles become negative. If the charge is too high, then the electrostatic repulsion is too large and the growth stops. So that is called the Coulomb barrier. Whether the bouncing barrier here that determines the pebble size is above or below the Coulomb barrier, of course, it's an important question, but that depends on the charging situation. And really nobody that I know of knows anything about that. That's just guessing. I think the empirical evidence that we're seeing pebbles in protoplanetary disks, we're seeing them in comets, speaks against the Coulomb barrier being smaller than the bouncing barrier. But who knows? It's not a stupid question at all.
Many questions. One, as you made, some people suggest that the smallest particles that we see in million years old disks are second generation dust, made of the destruction of larger bodies that generate this small dust, and that actually most of the planet formation has already started way before. In that case, from the scenario that you are proposing, I mean, we should observe this dust quite different, because it has gone through all these processes of compaction, saturation, and so on and so forth.
So you form the dust here, right?
Yeah, you would reform it. Yeah. So what would
somewhere here? Yeah.
Your prediction? I mean, what should be different if indeed this small dust comes from second generation dust and all the planets have been already formed? It's not the dust that will form the planets yet. Yeah.
I don't know.
Okay.
Good, really good question. Not necessarily. Of course, if these are the collisions you are talking about, they should all be compact. And that might change things. If we're here, in those cases, the pebbles don't change. The pebbles survive. Because they have internal strength of several kilopascals. Only if you overcome in the collision compression those strengths, you compactify them. But that's really a matter of simulation. So the best hydrocodes, they need an equation of state. And that is, I mean, this is the problem with the sand. There is no equation of state for sand at all. And there is no equation of state available for that material at the moment. We're working on that, but that is a question that might be addressed then at that point. But it's really good question, yeah. So this is all first generation thing I've been talking about. Yeah.
In particular, this is true for outer belt, all this outer region, cometesimal, planetesimal. But if we are going to the inner disk, probably we have larger particles, because of this catastrophic collision will be on differentiated bodies.
Yeah.
That perhaps are able to survive. A significant amount of the dust will be gone to the sun, and then remain some large rocks that
yes,
are able to survive. But in the other disk,
yes. I was in Nice last week and talking to Alessandro Morbidelli, and he showed me a paper from Ben Weiss, a review, and he claims that the lifetime of the inner disk is only 3 million years, and the lifetime of the outer disk is maybe 6 million years. So the 10 million years I'm giving here, or 1 to 10 million years I'm giving here, is maybe even exaggerated. So that might also play a role. If you only have 3 million years in the inner disk, whether you are going through different generations is a question then, and if you only have 6 million years in the outer disk, that's the same question. So it's really complex. As we discussed before in the other talk, we only can do simplified models, hoping that the complications by reality are not so severe that everything is falsified in the end. And this is why we are seeking evidence from real bodies.
We hear the talk. Thank you very much, Jürgen, for
Thank you very much for being here.